All right. So the introductions were very interesting. That was the first time I went to a meetup where people went around and introduced themselves. So I'm very happy to see how this is done. It's a great job. Uh, Hi, I'm Vishal, and I'm here to talk to you about how to deploy machine learning models in production. Before we get started, a bit about myself. I'm a machine learning infrastructure engineer at a startup called Cortex Labs. And my passion is the cloud. I work remotely, so my local host is in Toronto. I wish I could have transferred my packets over here via the internet. The ping would have just been a couple of milliseconds. But instead, it took me 5 hours from the Toronto hop to this hop, and I'm pretty sure my packets got sniffed along the way. That was a networking joke for people. Damn, that tough crowd. that killed in my company, but you know what? That's okay. I'm not here to make jokes about DevOps. I'm here to talk to you about how to deploy machine learning models in production. So let's get started. Now, I'm going to make a pretty general statement. Please don't fight me on this. I'm going to assume that this is a typical machine learning pipeline. Since you guys are here, chances are you guys are either interested in or are working in some section of this pipeline. So let's kind of just cover the basics a bit. Start off with your ETL. This is where you scrape your web data, you maybe get third-party data dump, you scour through logs, you transform the records and you load them onto a storage layer like S3, just so that you can kind of house it and it's pretty easy to access. And then you go on to your data engineering and your feature engineering. This is where you dive into your data analytics. You peek at your data. Maybe you have some float values, so you normalize them. Maybe you have some categorical strings, so you index them. Maybe you have some long text, so you tokenize them or convert them into bag of words. And you feed them into your model. Well, you haven't started your model yet, so you go into your model experimentation. You spin up a notebook, maybe a Colab notebook. You get that free GPU or TPU, and you try out different models, decision trees, neural networks, whatever floats your boat, and you tune your parameters, and eventually you get a model that has pretty good prediction accuracy, and you're like, okay, you know what? I need to integrate this into my applications. So how do you do that? Well, that's the topic of this presentation. It's model serving. Now, there's several ways to go about applying your model. You can do it in batch under the hood. Maybe you're doing analytics, so that serves that purpose. Maybe you want to deploy on the edge. But in this presentation, we're going to talk about how to expose your machine learning model as a web service to your clients. So at Cortex Labs, we realized that no matter where you're working on this pipeline, chances are your work culminates in a model file or a model weights file. And you need to get that to your user or your client. And so we decided to really hone in on this specific part of the pipeline. So chances are you have a model, you have a TensorFlow model, a PyTorch model, you've exported it to TensorFlow, Onyx, or you just exported the model weights. What exactly does it take to expose that as a web service? This is the part where it gets a little tricky. If you've spent your time building models, chances are you've been training up your stats and your math, and you're really head under the water under all the machine learning context, right? Now, all of a sudden, if you're expected to just go from the machine learning context and go into infrastructure, that's a pretty huge mind shift. Because when you get into infrastructure, you don't deal with hypertuning and things like that. You deal with, oh my God, I cannot SSH into my VM. Oh my God, I don't know, for some reason, this web request isn't able to connect to the instance, even though the instance is available. Like, the problems of DevOps, they're of totally different nature and kind of makes your head pull out sometimes. And I mean, I'm passionate about DevOps, and Exhibit A, this is what happens when you spend too much time in DevOps. And no, I'm kidding, that might just be a correlation, not a causation. But you guys can think about that, right? And so at Cortex Labs, we are passionate about machine learning, but our focus isn't on data engineering or actual machine learning, right? What we're good at is infrastructure. And so we decided to to create a platform to address this so that you guys can do what you guys want, which is the data science and the data analytics. But that doesn't necessarily mean that you shouldn't know how deploying a model works or what are the nuances of deploying a model in production. And so for the next 10 minutes, 10, 20 minutes, we'll go over what it takes to deploy a machine learning model in production. Now, chances are, if you have a model, you're able to run this locally, maybe on a notebook or on a Python file. You load your model, and you're able to run your inference in code. Right? Now, this is great, but you can't really access it on the internet. Right? So the first step is to convert this into a web service. And the way we do that is by wrapping your model inference code in a web application framework. Most people use Flask, so we'll stick with that. What Flask allows us to do is it allows us to wrap the inference code in a route so that you can access it. So for example, if you run a Flask server with the model inference code, you're able to go to your local host, 8080/predict. And then if you have a sentiment analysis model, you can say, I like this movie. And if you train it right, it returns positive, because in my books, that's positive. Right? So now it's working on your computer. The next step we need to do is we need to containerize it. The reason why we need to containerize it is the last thing you want to have is, it worked on my computer, I wonder why it didn't work on yours, or I wonder why it didn't work on the cloud. So to avoid that, we Dockerize it. Now, Docker is basically a factory, right? It's you build a template with all your requirements. So this can be your Python packages, your stitching libraries. Let's say if you want to run your model inference in a GPU, then you'd want to have the NVIDIA plugin or something like that. You include all that in your Docker file, and the Docker file becomes a template to reliably reproduce copies of your model serving of your model. Now, even after you Dockerize it, it's still on you can still run it on your computer. It's still available for you to run, right? Just as a side, for the rest of this presentation, I'm going to be referring to this containerized version of your web service as a replica. And for the simplicity, we're going to assume that one replica can handle one request from a client at a time, just to keep our math simple. All right. Now, we want to go to the cloud because that's where we like living. We like living in the cloud. Now, the cloud, you have your AWS, GCP, Azure. They provide different types of instances. The instances may vary from memory, CPU, GPU. So you need to choose the correct ones, right? And this is a function of the memory requirements, the compute requirements, and also how quickly you want to respond to a user request and how much money you're willing to spend. Right. So now once you choose a correct one, and this is kind of hard, you need to do some experimentation because only you know if you want to have one replica per instance or maybe multiple replicas per instance. So in this presentation, we're going to assume that you have multiple replicas per instance. Now we need to serve this to production. Chances are if you're deploying a web service, you need more than one request at a time. You need to serve more than one request at a time. So you deploy multiple instances. Right? Now this is a predicament. You have multiple instances that are running your web application. Which IP address, which URL does your client connect to? Right? They can connect to either one of them, but how do they know which ones to connect to? Now, to solve this problem, we're going to attach a load balancer. From the user's perspective, from the client's perspective, the load balancer represents a single point of entry into your entire application. Now, they don't care about how many instances that you have. All they care about is they sent a request to a URL and they got a response. Right? So now that's great for the user. For the maintainers, for the developers, this really helps you keep track of do the routing. Now, load balancer has several routing strategies. It basically maintains a map of all of the IP addresses and ports that are in your cluster, that cluster being multiple instances. And it uses a round-robin strategy. So that's one of the strategies. A round-robin strategy is where your user requests are routed to each instance equally. Another strategy for routing is, say, least used. When one replica is answering requests really quickly because the requests are short or something along those lines, it's probably more available. So then the load balancer can be a little smarter and direct requests to that replica. The load balancer takes care of routing internally. Now, we spun up 2 instances with 3 replicas each. Now, what happens if you're an Uber app and a concert just ends, right? You're going to have a spike in traffic of people calling Uber, right? And every time you call an Uber, Uber gives you a time estimate of how long that takes, right? Chances are that's a model, and that traffic is very spiky whenever a concert ends, whenever an event ends. That's why you have surge pricing and things like that, right? So if you have a consistent number of instances, you might not be able to accommodate that. Or if you do, then you're probably overspending during low periods. So this is when we add autoscaling to our infrastructure, right? And the autoscaler basically scales your infrastructure for you based on specific thresholds, based on metrics. So you can specify the autoscaler to have metrics based on the requests. You can have the autoscaler scale based on the CPU or memory usage requirements. Whichever the case is, the autoscaler kind of has an oversight of the cluster performance. And if the performance is exceeding a specific threshold, if the utilization is exceeding a specific threshold, then the autoscaler will allocate new instances. And conversely, if the usage falls below a specific threshold, the autoscaler scales down, right? And all of this works in conjunction with in unison with your load balancer, so that when a new instance is spun up, the load balancer automatically removes that memory mapping so that user requests don't get routed to instances that aren't there. And likewise, when a new instance is added, the load balancer is aware of these instances so that traffic can be directed to these new instances. Now, what happens if your autoscaler scales all the way down? This can happen if, let's say, in your web service, nobody accesses your web service for like 3 months, right? The autoscaler, if it's doing its job correctly, will scale all the way down, right? And this is where we have the cold start problem. It's where you have no replicas available, your user makes a request. And now what happens? So that remains in the load balancer queue, chances are, and that user has to wait until an instance is allocated, a Docker image is installed, the model is downloaded and loaded, and then you can fulfill that request. Now that might take anywhere from like 30 seconds to like 10 minutes, I don't know, depending on how large your model is. All right, so that's terrible user experience. So what we want to do is we want to set a minimum. Oops, sorry about that. We want to set a minimum. We want to make sure that the autoscaler doesn't scale down below a minimum number of replicas available, just so that you don't run into this cold start problem. Another way is kind of achieve the similar thing as a minimum, but a little bit more robust, is in your autoscaler, you configure it to have a buffer. Let's say a 15% buffer extra. So this means that you never scale down because you always want that extra 15% of whatever metrics that is. And the added advantage is that the autoscaler will now be capable of handling really spiky traffic. Now, we just mentioned that the autoscaling might take like 10 minutes to spin up an instance. What if your traffic is super spiky and in that 10 minutes, you get many user requests, right? So you want to have that buffer in between the autoscaling instances, just that extra buffer so that you can handle any overhead that you might have. Now, having that extra buffer, having some minimum, you're going to run into some infrastructure costs, right? And this is where spot instances come into play. Spot instances in the AWS universe are basically instances that are not used by AWS. They're owned by AWS, but users aren't using them, right? So they're leftover instances, and AWS gives them out at a markdown. So in this case, for these instances, you can go from anywhere to 40 to 70%. And the last 2 instances are GPU instances, right? So 70% off, that's amazing, right? The catch is that AWS can take them away at any time, right? In GCP, they're called preemptible instances. It's basically they loan them out to you, and whenever they feel like it's not beneficial for them, they take it away from you. Now, this can be problematic, but not for us because we've already put in the legwork. We've done our leg day. We did all the hard stuff, right? We have an autoscaler that can self-heal, and we have a load balancer that works in unison with the autoscaler, right? So even if an instance is interrupted and taken away, the autoscaler will just spin up a new instance so you can self-heal. And if you're over-provisioning, then you can handle that, right? So I just wanted to kind of raise an interesting point. Now, the difference between serving a machine learning model as a web service versus having an actual web service works in our advantage, right? When you have an actual web service, a website, you normally want to maintain a user session, right? So when you spin down an instance, you actually might have some performance. It might hit your performance, but because machine learning model serving, it's basically all copies of each other. It's okay if one goes down. They're basically all reads, right? The user requests are just making reads to your model. There's no state, they're stateless. So that's why it's very easy for you to spin up and spin down instances without actually impacting the user experience in any way. Now, so we built this in auto-scaling infrastructure. We need prediction monitoring for several reasons. We want to make sure that our autoscaler it's doing its work and the latency is meeting our standards. So we can monitor things like latency, we can monitor things like 400 or 500 errors, and we can raise alerts if they're exceed a specific threshold. We also want to make sure that our models are behaving correctly. Let's say if you have a fraud detection model, and the fraud detection model has been saying not fraud for the last 3 months, right? Chances are probably not right. Now, I don't work at a bank, so I don't know. I don't know how often fraud happens, but you'd want to know about that, right? So prediction monitoring helps you gauge the health and performance of your model and your cluster, right? But also, another advantage to prediction monitoring is that you can keep track, you can record your user input into your model, and you can also record how your model, what your model inference is, so that later on you can take a look at how your model is doing. Maybe it has a certain weak area, so you can tune your model to respond better to those kind of user requests. Now, let's say you've had alerts, you had some errors, right? How do you go about debugging that? Well, we add centralized logging to our infrastructure, right? And centralized logging is basically a one-stop shop where you can get access to all the logs from all your running instances so that you don't need to waste time figuring out, oh, this replica responded to this request in this way. I need to go and figure out where it ran, and then I need to SSH into it and get the logs, right? None of that. You can go into this one centralized logging platform, whatever that may be, and you can go about debugging your way. Right. Now we're going to talk about how we update our model serving. Right. Now this updating model serving can be a little tricky. Let's say you've deployed a model that has 90% accuracy, and over time you've improved it to 95% accuracy. You want to get that model out. There's several different deployment strategies. The one that we're going to talk about today is called the rolling update. And basically the way a rolling update works is you have your old web service replicas, you spin up a new one, and until that's healthy, the old web replicas are still answering requests. And the moment one of the newer version replicas is alive, you kill one of the old ones, right? So your old replicas are still responding to web requests. You still have uptime while you're doing a rolling update, but you're slowly building up to the newer versions, eventually until you replace all of your old models with your new model replicas. Now, what happens if there's an error? What happens if the model that you're trying to download isn't there? What happens if an intern deleted it by accident, right? So no problem, right? What happens since we do it one replica at a time, if we hit an error anywhere along the way, we can just roll back, right? And the reason we can do that is because we go one replica at a time, so we still don't have any downtime. Our web service is still active, but we can just remove all of the newer failed ones and replace it with the old ones. So let's take stock of the infrastructure that we built so far. We have a load balancer with auto scaling, and we have prediction monitoring and logging, and we can update our running models with different update strategies like rolling updates, other ones that are canary. You take your pick, right? Now this is a lot of moving parts. When you're a company like Uber or Google, you have the capital, you have the resources to be able to build robust model serving infrastructure, right? You might even build ones that are way better than the ones I just talked about. But what if you're a startup? What if you are a small company whose primary business is not in the machine learning space, but you're looking to leverage machine learning to augment your application, right? That can get pretty challenging because you have a lot of, not only do you have to build your model, which requires enough capital as it is, data scientists are not cheap, you also need to go about either training or hiring more machine learning engineers to deploy your models. Right? It's a lot of capital, it takes a lot of time, and there's a lot of decision processes that need to go into this. And that's why at Cortex Labs, we built an open source platform to address this. Right? Now, we're not the best data scientists or data engineers, but we're into infrastructure. So we built a platform that we think can be leveraged by startups and small companies, or medium companies, or large, up to you. And all you have to do is provide your model, and you can use our platform to deploy it as a web service. Basically, we believe that we can build it once, we can maintain it, and you guys can focus on what you do best, which is doing machine learning research, building new models. So how exactly does Cortex work? This is the anatomy of a Cortex cluster. So we have a user, and then the emoji or the picture at the bottom, that's the developers, 4 screens. I'm more of a one-screen user myself, but I hear that some people have many monitors. That's up to you guys. I don't know how you guys do all the multitasking. Anyway, so you have a CLI, a Cortex CLI, that basically helps you communicate with your cluster. And in the cluster itself, we have a Cortex operator. This is a process that manages the cluster and the workloads that are being scheduled on the cluster, and does some basic sanity checking for your input and things like that. Now you can notice that what we use in the Cortex cluster, those are all familiar names, right? You might be familiar with them. For the load balancer, we use the AWS ELB, and we use Istio for the network meshing. And we use for the autoscaling, we use Kubernetes deployment with AWS Autoscaling Group. And for prediction monitoring, we push our metrics to CloudWatch. And for logging, we use CloudWatch as well. So these are pretty standard stuff. What we do is we stitch them all together so that we can present a unified experience for model deployment, right? And this infrastructure runs on your AWS account. Currently, we only support AWS. And the important thing is that because it runs on your AWS account, you don't need to worry about privacy issues, right? None of the logs, none of the predictions, they leave your account. The models stay in your account. We provide the install scripts, so you don't need to worry about installing EKS or dealing with CloudFormation. Our script will set up the Kubernetes cluster and install the relevant workloads onto your Kubernetes cluster. Sorry, my voice is getting a little dry. And the way you interact with your cluster, the way you tell Cortex what you want to deploy is through YAML. So we decided to go with infrastructure as code, and this is how we did it. It might look familiar for a lot of you. It's declarative syntax. The reason why we chose that approach is we never want you to run into a situation where you ask yourself, what exactly is running on my cluster? If you want to know what's running on your cluster, just look at your YAML, right? And the YAML, the configuration, what we did was we tried to abstract away a lot of the infrastructure speak and try to give knobs that are intuitive and relevant to machine learning scientists, engineers, just so that they can go about, they can optimize their time. So let's kind of go into the knobs a bit. So you have your name, just the name of your API. It becomes part of the URL endpoint for your API. You have a model. Currently, with Cortex, we support TensorFlow exported models and Onyx exported models. And then you have your request handler. The request handler is basically a way for you to massage your user input and convert it into a way that your model expects. So this is your pre-processing. So often when you have like float or int, you might need to do some normalization, or you might need to convert the text into a bag of words. This is where you would do something like that. And similarly, when the model outputs a prediction, chances are it's in like a list of float values. You don't want to return that to a user. So you can have a post-inference handler, which basically converts your model output into an object or a response that makes sense for your client, something that your client would expect. And yeah.
So I have a question about this all seems really cool, but so who manages the Kubernetes cluster itself? Is it managed, when you say it's managed in your account, does it mean it's just spun up as an EKS something, or do you have to actually do it yourself? Do you have to actually deploy a Kubernetes cluster yourself?
No, so we have a script that deploys the EKS cluster in CloudFormation for you, right? And we're adding cluster tuning capabilities soon. That's on our roadmap. It's a good question. Yeah. So once you've defined your Cortex YAML, you just add it to the root of your repository, and you just do Cortex deploy. And what this command does is it packages up everything that's in the top level, wherever you define your cortex.yaml, packages that up and sends it to the Cortex operator, the operator that's running in the cluster. The operator does some sanity checking to make sure that let's say if you've defined a request handler, that the file actually exists. It checks that the model actually exists if it's in S3, does some basic checks, and then it orchestrates the workloads. Yes?
Quick question. Is this the command that builds the Docker image?
So we actually have Docker images that we use by default. We just kind of mount your project files into there. Does that make sense?
But it needs to all come into one Docker image to be deployed afterwards, right?
Mm-hmm.
Like your model has to go in somewhere to execute it.
Right. Yeah. So we have a stock Docker image for TensorFlow or Onyx, and then we have code. We run code there. Like we have our own Cortex Python code that downloads the model that you specified and packages up. And if you have a requirements.txt, installs that for you. Right. So it's a good question. Right. So now that you've maybe deployed, you want to optimize for developer time. You want to make sure that you can debug your models and your request handlers really easily. And you want to know what the state of your API is. So here we provide a dashboard of all the happenings of your API in CLI. So you can see the number of replicas that you have, the average latency that it takes, and then you can also see the distribution of, let's say if you have a classification, what the distribution is. And you also have we also mentioned your URL, so you can just take that and make dummy requests, test it out. And we also show you your model, the expected model input signature. Along a similar vein, we also provide a single way to stream all your logs. So even if when you're developing or iterating quickly, if you have multiple replicas, then we stream all the logs from a single API into one stream, just so that you can iterate quickly. So going back to the request handlers, right? So this is how we help you configure your API. We decouple your API from your model, Right? A common example of this, kind of going back to the NLP, is you wouldn't expect your user or your client to send you a bag of words or however you tokenize your text. Right? You want to do that in your pre-inference handler just so you can massage the data and prepare it for your model input. Similarly, when you return, you'd want to run your post-inference handler just so that the output is presentable. Right? You don't want to return a bunch of weights. You'd want to maybe take an argmax and return a label or something like that. Right. And we also built in escape hatches for flexibility. Now, with a lot of platforms come with opinions, right? They're like, we think that this is a good way to do things, right? And we also realize that just because we think it's a good way to do things, that might be the best for the average, but it might not be best for your case. So one of the ways that we help you escape our opinion is by allowing you to override the stock image that we provide. So you can just specify in an environment variable what your image is. As long as it complies with the interface that we're expecting, we'll run it. Similarly, for logs and predictions, we use statsd for our predictions, and we use fluentd for our logs. If you don't want to point them to CloudWatch metrics, then you can point your metrics to Prometheus or Datadog, and you can point your logs to Elasticsearch or S3, whichever. Right? Naturally, this takes in a little bit more customization work on your end, but it's possible just because you need to use we want you to use the technologies that work for you. All right. Okay, now we get into the demo. Okay, the SSH has timed out. We'll wait for that to come back. Right. Okay, at the back, let me know when you can see this. All right. Do I have a tree here? Oh, sweet, I have a tree. So this is your sample project. We'll assume that you have a model in your SRC. So let's see what that model is. So it's your classic iris example. There's a very poorly written model. I'm not a data scientist, so don't judge me. There's some training, and we export the model to Onyx. So let's run this real quick. Okay, 97% accuracy. Not bad if I do say so myself. Let's move this to S3. Let's see. Okay, we've uploaded our model to S3. So now we're ready to deploy our model. So let's take a look at the Cortex configuration that we have. So first we declare a deployment. A deployment is basically a unifying way to describe all the APIs that you want in a single package. So we're solving iris, so call the deployment iris. And the API, we're doing a classification, so we'll do a classifier. And this model, that's where we just put our model. Right? So now let's deploy it. So this command basically packages up all the files in the current repository, which is all these files. and puts them into a Docker image. There's a requirements.txt, so it installs that. It installs everything that requires requirements.txt. In this case, the requirements.txt is not too relevant for model serving, but it's there. So now let's take a look at what's happening. So the API is alive. Let's take a look at some more details. So this is the endpoint to your API. So here you can see the deployment name, and here you can see the classifier, and this is your load balancer. Right, there's one replica of it running. So let's make a request. So here we'll just do a curl. And for the model takes in an array with 4 elements. So let's send it an array. But before I do that, let me show you what's in the array. It's just an array of float values. So let's make the request, and it returns a list of floats, each corresponding to the confidence in one of the classes. This is probably not something you want to return to your user, right? The user they don't even know what this is. So let's add a request handler to make it a little bit more pretty. And okay, so you guys are gonna have to watch me add. And actually, you know what? Let me do this on this computer. Okay. Nope. All right, so it looks like I might have to do this in person. All right, bear with me, guys. It's, struggles of using Vim. Anybody? I'm not a Vim user, so hopefully somebody knows a shortcut. They can let me know. All right, so let's take stock of this. We added the request handler. We configured our. So let's take a look at what the request handler is. Pretty simple. So the API that we're expecting a dictionary key value pairs, key being the different feature names, and then we convert that into a list. And then for your post inference, we get the array of floats, we take an argmax, and then we return the actual label. All right, so let's do a deploy. So deployment is updating. It's updating. In the meantime, let's take a look at the logs. Let's see what the logs are saying. So here we have, so it indicates that we made one request, and it's spinning up a new instance. So while it's updating, the web service is still available, but it's the old web service. The request handler hasn't been, the model with the request handler hasn't been deployed yet. So while we're waiting for it to update, let's take a look. Oh, there it is. All right. So there's one stale web replica that's updating, and so in this curl we actually have a debug flag, and this debug flag basically helps you track what exactly the model is receiving and what the model is producing as an output. So there's a bit of a lag here. Okay, so it looks like the new web service is alive. Let's take a look at that. Okay, look, so we have one up to date. We have one stale, the stale being the old web replica. So let's try to make the old request. So the old request fails because we've changed the API of the API endpoint, right? And we can take a look at we can see that in the logs, right? Because we sent in an array, but we're actually expecting a dictionary. So let's change our curl to sample. But before I do this, let me show you what's inside. So that's what the sample looks like. So we get iris versus color, right? This is probably something a lot more presentable to the user. Right? And we get the latency, and we also get the 400 that we hit because we made an erroneous request. Now let's add a tracker just to make sure that we know the classes. So bear with me, guys. So we're going to try. So the model is a classification type, so it's going to look for string values in the return type. So let's deploy that. Oops. I think I screwed up here. And as part of this API, we specify the compute to be one CPU, so each replica gets one CPU. So the operator takes this and it recognizes that the configuration is different, so it does a rolling update again. In the meantime, does anybody have any questions while this is updating? Yes.
So for this, basically, I need AWS as a prerequisite and Docker, and then I need to install Cortex.
Yep, install Cortex on your cluster. I mean, on your AWS account. Yep.
Okay, and is Cortex available on Linux or all machines?
The CLI is available on Linux and Mac.
But no Windows?
No, not Windows. We don't do Windows right now. Unless there's an overwhelming request for it. Any other questions?
How do you handle the confidentiality of the models?
That's a good question.
How do you handle the confidentiality of the models?
Can you elaborate on that?
Well, if for example, does Cortex knows the models, or stays within the AWS?
It stays within your AWS account.
All right.
Right. So this is running on your AWS account. The S3 also on your AWS account. So when you create a Cortex cluster, you have to specify your AWS credentials. Right.
But if you want to use like deployment credential versus your actual credentials, do you handle that somewhere in the YAML file?
So currently we don't. You would have separate Cortex clusters. Yeah.
Well, I have a question. You showed a REST endpoint, right? But what if you want to deal with streaming data? Like, just as a question of like maybe read from a queue, write the output to a queue. Can I still use Cortex for that?
Not currently. Currently we support just JSON REST endpoints. Okay.
Have you compared to SageMaker?
Yeah, that's a good question. Yeah, we have compared it to SageMaker. And so for SageMaker, it kind of subsumes the model serving. It also has the model retraining and a couple of other features. What we heard from people who've mentioned that is people feel that SageMaker is a black box. They tend not to know what's happening under the hood. So for us, we are specifically solving just one problem, and it's just model serving, and it's all on open source, and we're using everything that you have control over. So I think that's where our priorities lie. Focus on the developer experience. I've actually never run SageMaker in production, so
it's about 1.5 times EC2 pricing. So.
Okay, well, thanks for that. I'll use that for the future.
When it comes to cost, is this supposed to be cheaper than SageMaker or other alternatives?
Well, we're adding support for spot instances, so that'll automatically make things cheaper. But we're not. Well, price is an important point. Our focus is just more on making it the easiest experience, right? And price is probably just maybe a byproduct of that. Okay, so the update is live. And then let's make a request. Right, so now that we added a tracker, it starts tracking the classes that you're predicting. So you can see here, iris first color, count 1. And so these metrics, they update live, just so you can keep track and iterate quickly. And yeah, that's pretty much the demo. Thank you. Where are we? Okay, let me put this up.
Hey,
So-
you have time for more questions, or?
Yeah, we have time for a couple more questions. So if you want to give feedback to me on how I did as a speaker, how relevant this was to you, I really appreciate it. If you just went to that link and just gave me some feedback. Yeah, this question.
Sure, thanks. Yeah, so just kind of curious, like I came to this presentation thinking kind of more of a broad, generalized context of serving models in production, not necessarily just using Cortex. Would you be able to give a little more context around some of the other alternatives besides Cortex, if it's just like setting up the infrastructure yourself, or are there other companies or other types of systems that would do something similar?
Right, so kind of going back to this slide here, if you wanted to set it up yourself, then you can use some of the tech stack that we listed here. And if you wanted more, kind of more managed, we already talked about SageMaker. And if you're familiar with Kubernetes, then maybe Kubeflow might be relevant to you.
Thanks.
Do you think it would be possible to deploy a machine learning model to a Lambda function, for example?
Yeah, so that is something that I think people are doing in generally, and that's kind of where the cold start problem is fairly prevalent. Just because I don't think that they've allowed you to configure, like, have certain lambdas up all the time. Right?
It's the idea, right?
I'm sorry?
It's against the...
Exactly, yeah. Yeah.
This model deployment, does it restrict the model type? Can be completely user-defined or just specific libraries?
Yeah, that's a good question. So right now, in this version, which is 0.9, we currently only support TensorFlow and Onyx, just because they're kind of self-contained. But we're in the next release, or the next few releases, we're going to add general deployment. So we basically just present an open API to you. You just need to specify these functions, and you can use Python. So for example, if you wanted to run, I don't know, an sklearn library, and you want to load it from a pickle, you can. And you can pretty much, the world is your oyster, basically.
So right now,
So right now, I think it's so the scikit-learn library is not supported.
Not out of the box, but scikit-learn you can convert to ONNX model format.
Okay.
Yeah.
Okay. And also the when user consume the model, do the model consumption, does it need to be do the ETL, all the you know, everything before you know, call this model, or can you can just input the raw data and all the way up to the result?
Oh, right. Yeah. So for this, I think if I understand your question, are you asking like, is the input to Cortex raw data or is it a model? Is that
Right. And feature engineering and data cleaning, that thing.
So the input to Cortex is a model that you've developed.
Okay.
So we're focusing strictly on model serving and optimizing that experience.
Okay.
I have a quick.
Hello.
Okay, so I was wondering, does this framework support A/B testing, like splitting traffic 50% for different versions of models?
Not yet. It's on the. That's also on the roadmap. We have plans to use technology like Istio, which does the traffic splitting for us. So it's there, and if more people ask, then we'll prioritize that. Yeah. We go by user feedback. Currently, people have been asking for spot instances, so that's also up next.
In the model you're using, in the demonstration, you're using HTTP requests. These are not HTTPS. Basically, you're sending an encrypted request to AWS. Does it work with HTTPS?
Yeah, you're right. So this is currently unverified. We currently don't, as of version 0.9, it's not, it doesn't support HTTPS in the correct way. But yeah, so if that's important to you, then we'll prioritize that.
Just to add to the previous gentleman's question about deployment. So I think what we're seeing here is about containers and Kubernetes, and that's kind of like one type of deployment. But you could also have other deployments in production from Microsoft SQL deployments, machine learning server, or to other kind of solutions as well.
Yep, thanks for the addition.
If no one else has a question, first, actually, I have a question about the open source project, the entire thing. So I know that cortex.dev is open source. Are you also getting help from people outside of your company to help you with the roadmap? Is the roadmap available for people to contribute to?
Yeah, so the roadmap. So we use GitHub issues for project management, and we have tickets representing using HTTPS correctly, or having spot instances, or supporting general model formats. And if any of those features are important to you, then you can just add a comment to those tickets, and we'll use that for when we're prioritizing. And if you want, you can contribute as well. It is open source, right?
So what do you exactly charge for?
Right now, nothing.
Free?
Yeah, it's free.
Okay.
Yeah. But yeah, it's free, guys. No catches. And if there are catches, you can find it because it's open source. It most definitely is on the roadmap. We just need to figure out how. Well, right now, we're thinking of going platform as a service. So right now, you once you install Cortex, you have to manage the cluster. But later on, that's kind of our monetization strategy, to manage.
I have one more. we don't use EKS. We actually have our own. We have our own Kubernetes cluster. Well, and based on your answer to my earlier question, like it seems like you basically spin it up and just kind of like abstract that out. Can you get cortex.dev to work on your own running cluster?
If it's on AWS and you modify some of the scripts, you can. Yeah, you just need to remove the part where it spins up an EKS cluster and just point your kubectl to the correct location.
Okay,
It should be possible.
Any more questions? All right, then let's thank our speaker.
Thank you very much. You've been a great audience. Lots of interesting questions.